Good morning. Wait a minute or two to get started here. Just give everyone else a chance to join. Feel free to let me know if you guys have any questions you want me to address. Was homework 5 due already? Okay. Well, I'm certainly welcome to address any questions about homework 5 you might have. I see that homework 6 isn't posted yet, so we obviously can't look at that. That doesn't mean I don't have lots of things to say. Okay, it was due on Monday. And I never know when the homeworks are due because it doesn't say on the assignment. I mean, obviously, I'm sure I could find it if I looked for it, but it's not super clear to me. Anyway, so are there any questions about homework 5? I guess I should start by saying, is there any? I'm happy to do them fully as they are if you would like. But if there aren't any questions about homework 5, we can certainly talk about other things. So for those of you just joining, I was asking if there were any questions about the homework that you guys turned in on Monday, which I'm happy to go over. Also, let me give you guys the, here's the attendance stuff. Attendance into, oh, that's interesting. So every time I pasted this in before, it hasn't come up as a link. And this time it did. I wonder what's up with that. Huh, I mean, I'm appreciative that it did. That just seems weird that this time it would and other times it hasn't. Interesting. Well, that's a pleasant change. Maybe it's an up. Actually, I remember I did. There was a Zoom update that I implemented, so maybe that was part of the update. Anyway, that's convenient. All right, I'm not hearing any questions about homework 5, which again I know was due, but just want to make sure there weren't any. Are there any questions about topics in general? I have a few ideas of things we could talk about, like where'd you go here? I mean, there's a lot of things we could talk about. I was thinking specifically related rates would probably be good to talk about, and yeah, that stuff. We can certainly talk about Newton's method and or Taylor polynomials and or linearization. I would give that stuff. I would talk. Sorry. Linearization is certainly important, more in this class than in other classes, because you definitely will see it again in 17C. Newton's method, less important. Taylor polynomials, occasionally important. But I would say of those 3 things, Newton's method, Taylor polynomials, and linearization is the one we should talk about the most. And then we should certainly talk about related rates. We should certainly talk about absolute extrema, which he is starting to talk about in class. So I guess I'll just start going. You guys, I mean, you can certainly request things if you have requests, but I think we should do some related rates problems because they are hard and it is something that we do quite a bit of in general. Let me minimize this. This is definitely some glare from my computer here. Can you guys, let me ask, can you guys see the glare? Is that glare on the board like terrible or is it kind of just whatever? I think I'm looking right at where I'm pointing right there. It's okay. All right. Good to know. All right. Let's do some related rates problems. Where the pen go? Okay. So once again, just as a reminder, we know something's a related rates problem when we are told how something is changing and asked how some related thing is changing. Here is an example. Yeah. Coffee drips from a cylindrical, not cylindrical, oh my God, a conical, sorry. A conical filter whose base radius is 4 inches and height is 6 inches. If the coffee, because right, because once it comes out of the filter, it's coffee, it's not just water. Or sorry, yeah, if the coffee drips out of the filter at a rate of, let's say, 10 cubic centimeters, 10 cubic inches per minute, how fast is the liquid level in the filter decreasing when the liquid is 2 inches deep? All right. And here's the attendance again for those of you who just joined us. So here's our related rates problem. We have some volume and it's filtering out of this cone-shaped thing. And we're asking, so we know the volume is changing, and we're asking how the water or liquid level is changing as the water drips out. So we should definitely draw a picture. So here's my cone-shaped filter. Kind of looks like this. And we have coffee dripping out the bottom. And we have, let's use a different color here. We have the liquid in here. And it's decreasing. So first things first. Well, actually, before I do that, I should probably label the things. So I'm going to call, in fact, let's do a little clear. Right, the radius of my conical filter is 4 inches. And the height of my conical filter is 6 inches. And the height of the water level or liquid level is changing, right? I'm not going to say, we're going to look at it when it's 2 inches deep, but generally I'm going to give it a variable name because it is something that is changing as time goes on. So I'm going to call that H for the height of the water. Okay, so now I know one thing is changing and I want to know how another thing is changing. I know how the volume is changing. dV dt is changing at 10 cubic inches per minute. Now, something to be aware of here, and it's mildly important, really just means you have to pay attention. Technically, in this case, dV dt should be negative 10 because the volume is getting smaller, right? When your volume of water is decreasing, the rate of change is negative. That means it's negative 10 cubic inches per minute. And we want to know what dH dt is. Can anyone tell me? Well, actually, I have two questions. First of all, should dH dt end up being negative or positive? You guys there? You listening? So I see someone has written positive, which is a perfectly fine guess. So what I'm thinking about is as time goes on, this water level is getting smaller, which means is the height getting bigger or smaller as we progress? The height is getting smaller. And if something's getting smaller, that means its rate of change is negative, right? It's changing at a negative rate. Because we're saying we're gonna get some answer like dH dt is maybe negative something. Well, actually, before I say that, let me ask you the second question I want to ask. What should the units be for dH dt? I'm talking about how the height is changing. Is it going to be inches per minute, inches squared per minute, or inches cubed per minute? So if it was inches squared, that would be an area per time. But height here is actually just a measure of length. So it's actually going to end up being inches per minute. but I appreciate the guess. Thank you for responding. You guys are very quiet today. You guys can also say words. It's perfectly fine. So I don't feel like I'm just talking to no one. So what I want to say here is that when we find dH/dt, it's going to end up being some negative inches per minute because the height is going to get smaller. Right? It's going to be the height's going to be 6 inches, and then 5 inches, and then 4 inches, and so the rate of change is going to be negative inches per minute because because we are decreasing. Okay, and we're going to need the other side of the board for sure. So we've got this. Ooh, too much. We've got a picture again here. Okay. So we know dV dt. We want to know dH dt. We need an equation relating the radius and the height of this cone. Sorry, not the radius, the volume and the height of this cone. So here's what we know, and I should say, right, it's really for this cone here, right, this small cone. We want to know what's the equation for the volume of that cone. Well, it's going to be volume equal to 1/3 pi r squared h. And that's always going to be the case, right? If you've got a cone, that's the volume equation. I think he gave it to you in the homework, I believe. It's probably something worth memorizing, as are most of these volume and area formulas. They often come up in these related rates questions. So there's an issue here. An issue that was less of an issue in the problem he gave in the homework because he kind of told you how things were correlated with each other or what the ratio is between the rates and the height. We don't actually know that explicitly here. So we have to figure out how to replace the radius here, right? Because I would like an equation that just had volume and height, right? Those are the two variables I want to relate, and they're the only two variables I want to relate. So what do? Well, I have to find an equation relating the height and the radius. And there's kind of a hard way. Well, there's an easy way to do this, and then there's a way that requires a little more thought. So here's the more thoughtful way. So I'm going to draw this again, but I'm going to cut it down the middle. I'm just going to draw it like a triangle. Whoops, sure. And the height of this triangle, right, this triangle here is 6, and the base of this triangle is 4. And then I've got this smaller triangle where the top of the water is, and the height of this triangle is h. And the base of this triangle is the radius. And so what I could do is I could use similar triangles to figure out how the radius and the height are related. I could say that I know I'm trying to solve for r because I want to get rid of r. So I can say the radius is to the height, right? The base is to the height as the base is to the height. So I can say that the radius is going to equal 2/3 of the height. Another way you can see this is literally saying if the radius of the big cone is 4 and the height of the big cone is 6, then the radius is 4/6 of the height because it's literally 4/6 of it, right? So that's the easier way, right? If you can just see the big cone, you're like, oh, there's always going to be this relationship. So then we're going to substitute that in for the radius here. So our volume is going to be 1/3 pi times 2/3 h quantity squared times h. And then before differentiating, right, because we're going to take the derivative so we can find the related rate, we're going to simplify this right-hand side. I can write this as 1/3 pi, 2/3 squared is 4/9, and h squared is h squared times h. And then 1/3 times 4/9 is 4/27 pi. H squared times h is h cubed. And now we're ready to take the derivative of both sides. So this was step 2, I guess. Step 3, differentiate both sides. The derivative of v with respect to t is dv dt. And the derivative of this, well, this is just a constant. So we get 4/27 pi And the derivative of h cubed is 3h squared times dh dt. Remember, h is just some function of time, so the derivative of some h cubed is 3 times my h squared times the derivative of my h, just like the chain rule every time. All right, so then we're going to plug in what we know. We know that dv dt is -10. And I'm going to plug in the units so you guys can see the units, so you can see that they work out the way that they should. And that's inches cubed per minute. And here, let's simplify a little bit. 3 and 27 can cancel and move the 9 on the bottom. I've got 4 pi over 9 times h. What was h? What did we say the height was? We're asking how the height is changing when the liquid is 2 inches deep. So the height should be 2 inches. So I'm going to get 2 inches quantity squared times dh dt. Now I'm going to solve for this. So look what happens. So here's what I've got. Sorry, that was a really nice noise. I've got -10 inches cubed per minute equal to 4 pi. 2 squared is also 4, so 4 pi times 4 is 16 pi over 9 inches squared times dh dt. Now I'm going to divide both sides by this. So I'm going to get -10 inches cubed per minute divided by 16 pi over 9 inches squared equals dh dt. And look, the units work out correctly. Inches cubed divided by inches squared, 2 of those inches cancel, and I get inches per minute. And then I'm going to flip and multiply, so I'm going to have -10 times 9 over 16 pi. And I can cancel a 2 here and a 2 here. To get -5 times 9 is -45 over 8 pi inches per minute. So that's how fast the water level or the depth is decreasing. So you could either say it's increasing at -45 over 8 pi inches per minute, or you could say it's decreasing at +45 over 8 pi inches per minute. The language there is kind of not the best. So questions about this example? It's okay if you don't have questions, but if you do, chime in. All right, I've got 2 more examples in mind. And then if you guys have other things you want to see, just let me know. Or before then. After these 2 examples, I'm going to start talking about linearization next, because of the things you guys are doing, I think that's the next most important thing. Okay. So here's another example. Yeah, let's do that. A 13-foot ladder slides down the side of a wall. Actually, sorry, slides away from the wall at a rate of 2 feet per second. How fast is the ladder moving down the wall when the bottom of the ladder is 5 feet from the wall? I kind of missed one keyword that might help this make more sense. I should have said the bottom of a 13-foot ladder. So the bottom or the base, the bottom of, a 13-foot ladder slides away from the wall at 2 feet per second. So here's what we've got going on. A lot of times, and I think some of this is my ability to write the question clearly. Some of this is just sometimes it's hard to interpret. It's always good to have a picture. So here's my wall, here's the floor, and I've got this ladder chilling right here, and it's 13 feet long. Also, here is the attendance again, whoever just joined. Attendance, and of course, the link to the tutoring. I'm so, like, I know it seems really stupid. I'm so pleased that now that it's a link and you guys can click on it instead of like having to copy and paste it, which I'm assuming you had to do before. It seems super annoying. So here's what we've got. We've got that the ladder is sliding away from the wall at 5 feet per second. So this length here, the length from the base of the ladder to the wall, this length is changing. And things that are changing in our related rate pictures have to get variable names. So I'm going to say that this length is x. In a similar way, this length is also changing, right? As the ladder slides this way, right, this length is going to change as well. So I'm going to call this length y. So I know what? I know how x is changing. I know that dx dt is equal to 2 feet per second. And I'm being asked what dy dt is, right? How is the top of the ladder moving down the wall? How fast is the top of the ladder moving down the wall when the bottom is 5 feet from the wall? So I'm trying to figure out what dy dt is. That's the big question here. And I think a lot like this part here, the drawing the picture and the kind of figure out what we know, what we want to know, is some of the more challenging part of these problems, right? It's just kind of figuring out what are we doing is what takes some thought. After that, it's usually not too awful. So let me ask you guys, I would like an answer. What kind of equation can I write relating the non-time variables x and y using my picture? Pretty famous theorem. You guys probably know it. It's mentioned in the Wizard of Oz. All right, we'll see how nobody is typing anything or saying anything. I'm referring to the Pythagorean theorem, which is in the Wizard of Oz when they're storming the castle or when he's trying to prove how smart he is. And you know, I'm not sure if he says it right or not. I should go watch it again. Actually, it's not that great a movie. I should go watch that one part again. So the equation I'm looking for here is x squared plus y squared equal to 13 squared. That is definitely how x and y are related in this picture. And it's because it's a right triangle, because we're assuming, of course, that the wall meets the ground at a right angle. Right? That's what we'd certainly hope for. And then we're going to differentiate both sides. And again, this is a lot like implicit differentiation. We're using the chain rule. The derivative of x squared is 2x times dx dt. The derivative of y squared is 2y times dy dt. And what's the derivative of 13 squared? Yeah, thanks. And so then we're going to plug in what we know and solve for what we don't. We know that dx dt is 2 feet per second. So we get 2 times x. I also know what x is, right? Because I'm asked how fast it's moving when the bottom of the ladder is 5 feet from the wall. So this is our x value. So x is 5 feet. Dx dt is 2 feet per second. And y we'll figure out in a minute here. Dy dt is what we're trying to figure out. So we're at the moment in time of this ladder sliding down the wall where x is 5. And we can definitely use the Pythagorean theorem to figure out what the y value is. Does anybody know what the y value is just off the top of their head without using the Pythagorean theorem? There's definitely a Pythagorean triangle that's 5 something 13. It's a good one to memorize. or did, like, we have the 3, 4, 5, and the multiples of it, like 6, 8, 10. There's also a 5, 12, 13 Pythagorean triple. Right, so this value is going to be 12. Because if you try to solve this, 5 squared plus y squared equal to 13 squared, that's going to be y squared equal to 13 squared is 169, 5 squared is 25, and the difference there is 144. So y is going to equal 12. So that's what's going to go in over here. 12 feet. Yeah, 12. And so then we're going to solve for dy dt. So I would bring all of this over to the other side. So I have 2 times 12 is 24 feet times dy dt equals, bring this over to be negative, 2 times 5 times 2 is negative 20. Well, 2 times 5 times 2 is 20, and then it's negative. So it's negative 20 feet squared per second. And I'm going to divide by 24 feet. So I'm going to get dy dt equal to negative 20 feet squared per second divided by 24 feet. One of the feet cancels, and end up with negative 20 over 24, which reduces to negative 5 over 6 feet per second. Couple things here. One, it does, oh, how did I get to 24? By doing the 2 times the 12. Right, because y, right? So I have the 2y dy dt, and I have my 12. Let's hang this over here. But I plugged in y equal to 12, which we just solved for. And I have 2 times 12 to get 24. Hopefully that is clear. A couple things about our answer. One, it does make sense that it's negative because the value of y is getting smaller. So dy dt should be negative. Yeah, exactly, right. I moved this over, right? Because I was like, I wanted to keep the dy dt having a positive coefficient, because if I'm trying to solve for dy dt, I would rather not divide by negative. You could have done either one, really. So yeah, I moved this over to that side. It was negative 20, and then divided by the 24. That was right there. So it does make sense that it's negative. And the other thing is, so you'll notice I was writing the units in the whole time. I don't think you need to do that. I think it's way, so if I was actually doing this problem like on my own, here's how I would have done the work here. So just so you guys can see how I would have actually done this. So from this step here, right, if I have 2, this kind is not great, 2x, that's dx dt, plus 2y dy dt equal to 0. When I plug in, so I know that x is 5, so I have 2 times 5, dx dt was 2, and then 2 times y was 12, and dy dt was what we're trying to solve for. I'm going to bring this to the other side, so that's about 2 times 5 times 2 is 20, so it's negative 20. So I end up with negative 20 on the right, and 2 times 12 is 24 dy dt. And then divide by 24 to get dy dt equal to negative 20 over 24, which is negative 5, 6. And then to fill in the units, I would just ask what makes sense. Do I have a length, an area, or a volume that's changing? Well, in this case, it's definitely a length that is changing. So my units should be feet per time. Not feet squared, not feet cubed, but just feet. Or whatever your unit of measurement is, right? If it was meters, it would be meters per second. If it was miles, it would be miles per whatever time. So just use the units that we're giving you. In this case, it was feet per second. We're going to have feet per second. On the other hand, if it was some area that was changing, then I would know it should be feet squared per second. Okay. Yeah, let's do, I think, so should we do more related rates or should we move on? I could certainly do more, but I feel like it's probably worth moving on to linearizations. But if you would like to see more, okay. So I have one vote for moving on. I will say, whoever speaks up, right? If you speak up and nobody else says, you get what you want. Okay, so let's talk about linearizations. And this actually is a, I will say, I'm also doing a Co-17A class right now, and it definitely comes up. We definitely talk about linearizing functions of two variables in 17C. For now, we're just going to talk about linearizing functions of one variable, but I will stress that it's something you want to make sure you understand. And it's also not something that's too terrible to understand. It's a concept I think that after some practice is pretty straightforward to make sense of. So the idea of a linearization is literally that we are going to linearize a function at a particular point, meaning we're going to approximate a function with a straight line. So let's look at a pretty standard example. Let's look at, say, y equal to the square root of x, and we're going to linearize this, linearize at the point, you sometimes be able to say x equal to 4, or you can find the y value as well. Let's say it's 4, 2. So x equal to 4, aka at 4, 2. And you know what? I could try and draw a picture of this, and I will, but I could also do it on Desmos. So let's just take a look at Desmos real quick here, just so you guys can take a look at this. I think it's worth having a nice picture. Let me grab this here. Sorry, 1 second. That's not what I wanted. Come on over here. Let's see, graphing stuff. Desmos. Okay, so let me share my screen. Okay, so here's the y equals square root of x function, which I'm sure I know how to do. Yeah, there we go. And so we actually have to find the linearization, which I suppose I should have done before I just got crazy. But the idea is we want to find the equation of the line tangent to this function at the point 4, 2. So we're trying to find the equation of the tangent line right there, which I guess I don't actually know what that is yet, so we should do the linearization. But actually that's kind of something that's important to recognize, is that when someone says linearization, at least in regular two-dimensional graphing, all they mean is find the equation of the tangent line. So I'm going to find the equation of the tangent line. I need two things. I need a point, got it. I need a slope, I can find it. So to find the slope, it's going to be, let's see, I need the derivative. So if my function is y equal to x to the 1/2, my derivative is, let's see, 1/2 x to the minus 1/2. And then I'm going to plug in my point. So I'm going to plug in x equal to 4. So it might have been better to call this f of x, right? F of x is x to the 1/2. F prime of x is 1/2 x to the minus 1/2. Or I would rather write this as 1/2 times x to the 1/2, or 1/2 times the square root of x. That's actually my preferred way of writing the derivative of the square root of x. So then, if we plug in 4, f prime of 4 is going to be 1/2 times the square root of 4, which is just 1/2 times 2, which is 1/4. So that's our slope. And so then the equation of our line, well, we don't have the equation of line, it's going to be y minus the y coordinate equal to 1/4 times x minus the x coordinate. And now here's something that's interesting about linearizations. We do have to solve for y, but we don't write it in the y equals mx plus b form typically. So the right way to do this, the standard way to do this, is to say, okay, I'm going to have y equal to 2 plus 1/4 times x minus 4. And we usually just leave it like that. So typically we would write that the linearization, which we use capital L of x, is equal to the function 2 plus 1, the straight line, 2 plus 1/4 times x minus 4. Okay, let's go back to Desmos and graph this. So I've got y, sorry, to do the thing, share screen, share this. So look, I've got y equal to 2 plus 1/4 times x minus 4. And that is exactly giving us the tangent line at the point 4, 2. Let's zoom in there. Right, so right there, it's just, they're just touching, and anywhere over here is different. So why would you do this? Well, one of the reasons you would do this is so that then you can approximate the function at other values. So for example, let's say I wanted to find the square root of 5. Well, if I had a calculator, I could totally just plug it in, and right there, if I plug in 5 to the square root function, which is the red function, I'm getting approximately 2.236. It's not an exact value, it's an approximation. On the other hand, if I plug in 5 to the linearization, which I could totally do without a calculator, right? If I plug in 5 for x, I get 2 plus 1/4 times 5 minus 4. Okay, 2 plus 1/4 times 1 is 2.25, which I should get if I go to 5. If I get on the blue function, sorry, they're so close to each other, I get 2.25. So look, we can use this linearization. This is the whole idea. We can use this linearization to approximate the function pretty well, right? I mean, 2.2, sorry, I'm on the blue one there. They're too close to each other. Can't get off the blue one. Give me the red one. Why won't we? Oh, I'm smart. I have to click on the right function. Sorry. Okay. So, right, we said we had 2.25, and this is 2.236. That's a pretty good approximation, I think. So this is definitely the idea behind a linearization. Is that you can use this linearization to approximate a nonlinear function at points that are close to linearization. Now, let me actually go back to the screen sharing for just 1 second, because I want to point out at 5, this is a perfectly good approximation, right? 2.25 is a really good approximation of 2.236 or whatever. But if you go far away, our approximation gets less good, right? Over here, it's like if I was trying to find the square root of 2, right? The square root of 2 is about, well, not about, it's about 1.4, whereas our approximation is giving us, like 2, I think, or 1.5. Still not bad, but right, as we move further away from the point of tangency, from where we are doing the linearization, we get less good approximations, right? And if we move further out, we can see like way over here, if I was trying to approximate the square root of 20, right? My linearization is giving me a value of 6, whereas my actual square root is giving me a value of about 4.47. So linearizations are good approximations near the point where we are linearizing at. And as we move further away from there, not so good. So let me stop sharing. Okay. So usually, and I can't necessarily speak for Sandra, so I don't know what kind of question he's actually going to ask. But a lot of the times people ask something like, say something like, find the linearization of this function at a particular point and then use it to approximate something. So here's what I'm going to say. I'm going to say use, and we'll use square root of, let's make it more fun. Let's use cube root. Use a linearization of f of x equal to the cube root of x. So when I read these words, what I'm really thinking is, oh, they want me to find the equation of a tangent line to approximate the cube root of 10. Okay, cube root of 10, sure, why not? Yeah. So something to notice here. They didn't tell you where to linearize the function at, right? They didn't. The previous problem, linearize x equals 4, linearize y equals square root of x at x equals 4. So we found the equation of the tangent line, and then we used that. So what we did, we used this to approximate the square root of 5, and we got approximately 2.25, whereas the actual value is about 2.236, I think it was. I don't remember. So same idea here, except now we have to work a little bit harder because we figure out where should we linearize this function? What's a good value of x to plug in that is easy to evaluate and close to the thing we're trying to actually approximate? So any guesses, you guys? What's a good value of x that's close to 10, that's easy to take the cube root of? It's my favorite number, by the way. So I wouldn't say 3 because I don't know what the cube root of 3 is. 9 would be good for a square root because the square root of 9 is 3. What's a good number that I can take the cube root of? So I think you mean 2 like you meant 3. I actually think you mean 8, exactly. Yes, 8 is my favorite number because I was born on 8/8. But yeah, so and really the way we figure out what number to plug in here is we say, well, obviously I want to plug in a cubic number. So I'm just going to start looking at cubic numbers, 1 cubed, 2 cubed, 3 cubed, and see which one is closest to 10. That's 1, that's 8, that's 27. Clearly it's this one. So we're going to linearize at x equal to 8. Now here are, and sometimes people use a instead of x, which is perfectly fine. Sorry, I got the hiccups a little bit. So here's what you have to remember. We're just finding the equation of the tangent line. So I need a point. Okay, well, I'm using a or x equal to 8. So my point is going to be a comma f of a, which in this case is 8 comma f of 8, which is 8 comma 2. And then we need the slope, which we're going to get by doing the derivative. So my function is the cube root of x, which is x to the 1/3. My derivative is 1/3 x to the negative 2/3. And again, I would really rather write this as 1/3 times x to the positive 2/3. Okay, that's the derivative anywhere. How did I get 2 for f of a? So my function is f of x equal to the cube root of x. If a is 8, f of 8 is really the cube root of 8, which is 2. So then we're going to find the derivative, but we need to find the derivative at our point of interest. So I'm going to find f prime of 8, which is going to be, which is my f prime of a. So there's something I'm leading up to, so I should do. So f prime of a, which is f prime of 8, is 1/3 times 8 to the 2/3. And 1/8, 3 times 8 to the 2/3 shouldn't be too terrible to calculate. Right? We know that 8 to the 1/3, right? We just did this, right? Cube root of 8, which is 8 to the 1/3 power, is just 2. So, what am I trying to say here? Sorry. So if 8 to the 1/3 is 2, 8 to the 2/3 is 8 to the 1/3, which is 2, and then squared, which is 4, and then times 3, which is 12. So I get 1/12. And that's my slope. So I typically still go back to the y minus my y value equal to my slope times x minus my x value. But then we always want to solve for y. So for these ones specifically, the linearizations, we have to solve for y. So y equals 2 plus 1/12 times x minus 8. And then we rewrite it as L of x equal to 2. So there's our linearization. And again, all I'm saying there, just using a different word, is there's the tangent line to this function at x equal to 8. One thing I want to point out, I'm going to erase this over here. So let me actually, and I'll write this over, right? We had a equals 8, and we found that f of 8 is the cube root of 8, which is 2. So people will often memorize the kind of, I guess, formula or the way that the linearization looks. So here's how linearization always goes. L of x is equal to f of a plus f prime of a times x minus a. Right, all this is the equation of the tangent line, just written differently. Right? Really, this is just coming from, right? If I rewrite this, this is choose a different color. Right, this is L of x minus f of a equals f prime of a times x minus a, or if you prefer, this is y minus your y value equal to your slope times x minus your x value. So it's really, really just the equation of the tangent line. It's just people like to write it like this and memorize it like this. So you will almost very likely see someone say something like this, or have seen someone say something like this at some point. All right, we're not quite done though, because so we found the linearization, which means we found the equation of the tangent line. Now we actually have to plug in. So let me erase this stuff here. And so here's the point. The linearization is an approximation of the function near 8. So what we're saying is that f of x is approximately L of x for values of x close to 8, where we're not going to define what close means. And so here what we're saying is, okay, the cube root of 10, that's really squeaky all of a sudden. The cube root of 10 is approximately the linearization at 10, which is going to be, I'm just going to plug in 10 to my linearization. So L of 10 is going to be 2 plus 112 times 10 minus 8, which is 2 plus 112 times 2, which is 2 plus 1/6, which you could either write as a improper fraction, 13/6, or you could write it as a decimal, which is 2.16 forever. And then you could, if you want, you can compare that to the actual value. So if you look on your calculator, the cube root of 10 is going to be, let's see, I get 2.1544 approximately. So pretty good, right? Right to the first decimal. So this is the idea of linearizations in a nutshell, right? You're just finding the equation of the tangent line, and then you're using that equation of the tangent line to plug in a particular value that you want to try and estimate that. Let's do one more. We've got a little bit of time. This next one won't, whoops, wow. Next one won't take very long. So I want to use a linearization to approximate or if it looks extra like loose. Approximate 1.02 to the 13th power, 1.08 to the 13th power. And while this seems like a giant pain, right? You could totally multiply this out. It would be not fun, but you could do it. However, you can say, well, so here they didn't even give us a function. So the function you're going to do is this going to be take whatever number you've got in here and replace that with x. So our function is going to be x to the 8th, 13th, sorry. We have to identify a couple other things. We need to figure out our a value. So what's the value of a, or x? What's the value that's close to 1.08 that's easy to actually evaluate? The answer should be, I think, be really, really obvious. It's a number that's really, really close to 1.08. It's really easy to raise to the 13th power. One. So our a value is 1. F of a is f of 1, which is 1 to the 13th power. And then the derivative is 13x to the 12th. So f prime of a, which is f prime of 1, is just going to be 13. So here's what our linearization is going to look like. L of x is going to be f of a plus f prime of a times x minus a. So that's going to be f of a is 1, f prime of a is 13, times x minus a, and a again was 1. So there's the linearization, right? This is the function that is approximating this function for values of x near 1, or values of a near 1, values of x. And then we're going to say, okay, well, 1.08 to the 13th power is approximately the linearization at 1.08, and then we're just going to plug in 1.08 for x. And the reason it's kind of written this way is so that you recognize that whatever you've got here is going to be relatively small. So I'm ending up with 1 plus 13 times 0.08. And 13 times 0.08 is something. It's 1.04. So I end up with 2.04. Whereas if we use the calculator to actually do 1.08 to the 13th power, we'd end up with 2.719. So clearly our value was maybe a little too far from the actual point to get a good approximation, but it's not terrible. Or my math is wrong. Let me make sure that I multiplied 13 times 0.08 correctly. Nope, that's right, okay. All right, everybody, that's all I've got for today. I imagine on Friday, we'll probably look at whatever he's got on the homework and go from there. But in the meantime, if you have any questions, let me know and I will try to address them. Hope you guys are doing all right. You're very welcome.